Okay, folks, this is the start of the N02 lecture on uranium mining from myself, Alison Robinson. So yes, it's the start of the nuclear fuel cycle. You can't have any of the nuclear fuel cycle clearly until you've actually managed to get uranium or whatever it is you're after out of the ground. So there's a couple of really good information sources on uranium mining. The first and best one is the actual World Nuclear Information Library that you can access through this link here. This I think is the best one. It's updated annually. What you get annually does change slightly over time, but it is it's pertinent, short, interesting, and to the point. You also have the IEA's Red Book. That's this document over here. They again publish that annually. It's good bedtime reading if you suffer from insomnia, but it does have a kind of inside that. So these are kind of the two key information sources from all subjects pertaining to uranium mining. Okay, so uranium's a mineral. It occurs naturally in the rocks, in the ground. And it's got a kind of average abundance in the Earth's crust, on average, of around 3 parts per million. That actually, interestingly, means it's less abundant than gold, silver, or mercury, and slightly less abundant than cobalt, lead, or molybdenum, which is all very well. Uranium has some unusual properties as a mineral. It's kind of quite a large mineral. It's got a large ionic size, and that means that it behaves slightly peculiarly in rocks, particularly in liquid igneous rocks. So igneous rocks are basically liquid rocks that come out of volcanoes, and when you get liquid igneous rocks coming out of volcanoes that have basically got uranium dissolved into that liquid there, that uranium is one of the last components to solidify into the rock mass as it cools. Liquid rocks essentially come out hot, they cool, they crystallize, and they become solid over a period of geological time. So uranium, because of this ionic size, large ionic size, it's one of the last elements to kind of crystallize out from that cooling liquid rock. And that large ionic size also means that it's one of the first that melts if that rock gets heated up again, because you can have rocks reliquefying because they get heated. And the point about this kind of mobility, as it's usually called, is that it explains why you get some uranium ore bodies. Not all of them, but it does kind of explain some of them. So top right of the page, you've basically got some stats on uranium. Mineral hardness, around 6. It's kind of in the middle there. Neither particularly soft nor particularly hard, just really kind of about average. Bottom right, you've kind of got a picture of some uranium ore. Pictures don't really say a lot because there are many different forms of uranium minerals. They can all look quite similar, brown, various shades of brown, slightly different shapes depending on how the rock's been kind of broken out. So the pictures aren't particularly good to identify these with. At the bottom of the page here, you've got 2 links to a very good UK website called virtualmicroscope.org. So if you go on Virtual Microscope, you can basically have a look at different mineral specimens and rock specimens. It's a really useful expanding website with lots of visual information on different rock and mineral types. And they've got some photographs of uranite and some photographs of basotite, which are 2 different types of some of the many uranium minerals that you have. So looking at this slide here, you've got some different uranium minerals in here: uraninite, pitchblende, colfinite, brannerite, carnotite, and urethane. I'm skipping out that one there. I've no idea how to pronounce these. These are all very, very slightly different mineralogical forms, and you find these occurring in different types of rock. And these ones here in this bottom picture, they're the most common forms. So there are actually more forms than these. These are just the most common ones that you're most likely to have. Of these kind of different rocks that actually host uranium minerals, they can easily be divided into 3 different types. And I've kind of done this over here for you on the bottom right hand side of the page. You have magmatic rocks, hydrothermal rocks, and sedimentary hosted type rocks. So what are these? Well, magmatic rocks are basically rocks that come up in liquid form, carrying uranium minerals above or round about the Earth's surface, the actual top level of the Earth's crust, and there they solidify and the uranium crystallizes out as they cool and solidify. Hydrothermal rocks is where you basically get hot fluids being injected into different rock types at any one location, and fluids are uranium, some form of uranium mineral, along with the rest of that hot fluid. So when it comes to kind of considering uranium mobility and that last to crystallize and first to melt type property of uranium, it's categories number 1 and categories number 2 where that applies to. So uranium with magmatic and hydrothermal fluids will be the last to crystallize and the first to melt out should these rocks be reheated. So basically, uranium in relation to these 2 rocks types is basically quite mobile in the environment. If it gets heated again, it'll be off like a shot somewhere else. Your sort of final category in here is what you call your sedimentary hosted uranium mineralization. So sedimentary rocks are a category of rocks made out of detrital debris that's been eroded from elsewhere. So sedimentary rocks are typically made out of sandstone, can also be made out of clay-sized particles and silt-sized particles as well. But for the purposes of uranium mineralization, you're solely talking about sandstones. So if you think about perhaps your typical image of either Blackpool or Southport Beach, just a kind of flat layer of sand, several meters deep, or if you think about kind of the Sahara Desert or even sort of Arizona desert, etc., vast expanses filled full of sand, that's kind of perhaps sand in the making. If those areas of sand get changed into rock, they're basically going to create a sandstone. And if that sandstone kind of gets impregnated with uranium minerals, then there you go, there you've got your sedimentary hosted uranium. And it's a fairly common form of uranium mineralization. So World Nuclear kind of each year updates its table on which countries kind of producing the most uranium from different mines. It does this first by country, and we'll have a look at it later on by individual mine. So here you've got at the top of the table Kazakhstan and Canada. They usually kind of hold the top 2 spots and occasionally swap it about. But if you kind of look at this, Kazakhstan producing from multiple mines has been outproducing Canada as a sort of country for quite a few years now, where Canada is basically putting up its production, but It still hasn't beaten Kazakhstan yet. Right, so resources. Resources are basically how uranium's categorized. To some extent, you could think that resources are finite, and it's one way to kind of think about resources. Once they're used up, they'll be used up. But geologically speaking, there's kind of plenty of areas of the Earth that haven't been fully explored. So there is a possibility of actually discovering more uranium on planet Earth at some point in the future. Why hasn't the Earth been fully explored? Well, you've got cases like Greenland, where you've got Greenland being covered by a massive ice sheet, so you can't explore underneath that. And then you've got the simple fact that geological exploration costs money. And it's also not the easiest thing to do in remote areas. So if you consider the UK is kind of the first country to get geologically mapped. The UK was largely mapped by Victorian geologists working off horseback. So they would basically be assigned an area of the country, they would explore it on horseback, and they would map out the geology. And that ever since has been tweaked in areas known to be slightly erroneous by the British Geological Survey. So that's kind of quite a high cost, and even when you kind of put technology in there and think about aerial surveys, that's still a huge financial outlay, and that explains why some countries just have kind of quite sketchy information on what deposits they have, what their geology is. So it's really down to kind of finance. So there is a potential for future discoveries to be made. As you can see with oil and gas, up until this year, there's been quite a demand for oil and gas. So you'll see popping up in the news, you know, massive oil and gas deposits having been discovered and soon going to be exploited if the market price makes it viable. Would say that availability of uraniums had quite an impact on the UK. If you consider what the United Kingdom and Atomic Energy Authority, UKEA, was doing up at the Dounreay Nuclear Research Establishment, they were basically exploring fast breeder reactor technology. The reason that they commenced that in the 1950s was that in the 1950s there was thought to be a shortage of uranium on planet Earth. So the UK government thought that leading research into fast breeder reactors was a good thing to do, because ultimately they breed fuel within their cores and hence they need less uranium to run them overall. But unfortunately for Dounreay, in the 1960s, these vast deposits of uranium were discovered both in Canada and in Australia, which are clearly kind of Western Commonwealth member countries. And so the global shortage of uranium kind of disappeared, to be quite honest, which kind of was one of the reasons why fast breeder technology was later abandoned by the UK, although it's been picked up recently by the EU and by India, and I think possibly South Africa as well. So perhaps put on hold is a better description of that. So yeah, the availability of uranium has definitely kind of influenced the historic nuclear program in the UK. So if you have a look at these maps here, they're basically from the Red Book, a mixture of 2018 and 2019. And this large one here basically shows you where on the globe they've identified the large part of uranium resources. And in here you can see Australia. Australia at the moment holding the largest part of identified resources for uranium. Although if you look at the pie chart top right here, Again, look at Kazakhstan. This is Kazakhstan. Kazakhstan's taking just under half of the uranium production for 2018. Why is this? Well, it could be that it's their only money earner, to be quite honest. I don't quite know. But obviously with the Russian Federation, you've kind of got quite a big customer on your market, on your doorstep, as it were. So resources. Resources, you have to be careful about this term, because depending on what you're reading, there's actually, people may have different definitions for resources. So if you talk to an ore geologist dealing with kind of ores, how you get them out of the ground and things like that, they go with number one. Number one is the traditional definition of a resource. It's the amount of material or resource available to be extracted in an economically feasible manner. So it isn't the total resource. It's basically only the material that can be economically extracted. But you find the other definitions being used, and the Red Book talks about reasonably assured or identified resources. So it doesn't necessarily use this economical, economy-based definition. And you can also talk about the total amount of resource, but this then assumes that everything's been discovered on planet Earth. So number two is possibly not the bestest definition. But to return to this economically feasible manner, whatever mining company is undertaking extraction of ore X, it's got to be economic to them. You know, it's got to be able to be sold on the open market in a profitable manner. If they're not making a profit, then they're not going to make a, you know, it's not going to be cost effective to basically get it out of the ground. So they're not going to do that. That's the way that economics works, and it's kind of worth kind of keeping an eye on kind of energy pages and market pages in one of the better newspapers to kind of follow what's hot and what's not. So uranium resources over here on the right hand side, there you can see Australia coming in at the top there, and then just Kazakhstan there, and then Canada just a little bit further behind in there. And some kind of unusual countries in here, Tanzania and Jordan down there, and Botswana as well, which are kind of unusual to think about uranium for uranium supplies in relation to that. But just bear in mind, when it comes to resources, whatever you're reading, make sure that you understand what they are defining as resources, because it's not necessarily the same across all parties. The IAEA have various documents on uranium and uranium mining, and some links to these at the back. One of their key texts, however, identifies 14 different depositional environments or geological environments in which you can get uranium being deposited. And this is some of the list here on the right hand side of the page, all these different types of deposits. And we'll have a look at them. These ones on the right hand side are perhaps the more important of these. But not all of these are worked. What you have to think about in relation to those economical factors is the quality of the ore, the concentration of the ore, and the costs of actually mining it out of the ground. So if your ore is quite low in terms of parts per million, you know, if it's quite a low grade of content of uranium, and so you've got to remove a lot of rock to get a relatively small amount of uranium out of it, then that's not going to be as profitable if the uranium is kind of concentrated in one small geographical area. It's going to kind of put up your processing and your handling and your excavation costs, and it's going to make it uneconomic. So you've kind of got to tie all of these factors in and think about what the market price is for uranium. And that's often what makes some of these different types profitable or not profitable as the market price fluctuates. It's very similar for oil and gas, but obviously at the moment there is kind of a bigger global long-term market for oil and gas, at least globally there is, maybe not in Western Europe as it looks to electrification, whereas uranium, you've kind of got only so many customers, and things like the Ploughshare program, reusing nuclear weapons, etc., have definitely over recent years put a dent in, well, a small dent in the global demand for uranium. So let's kind of have a quick look at the geology, and we're not going to get too deep on this, but just to kind of give you a background understanding. Geology can be divided into two types: your superficial geology and your solid geology. So your solid geology is basically what most people think of as geology, can also be called bedrock geology. So this is the actual genuine solid rock. So this is solid rock that's generated from liquid rock coming out of the center of the earth, think volcanoes and lava, that solidifies to form solid geology. Or it could be other types of sediments becoming rock, or it could be existing rock that's being metamorphosed into a different rock type by the application of heat, pressure, or chemicals. So your solid geology or your bedrock geology is what most people think of as being geology. But sitting on top of that, and it's always on top of that, you basically have a type of geology called superficial geology. And this is basically not actually solid. It's not actually rock yet. It's a series of sediments, of detrital debris, that come out of erosion and transported debris. So basically you have solid geology. Think about Everest, Scafell, or Ben Nevis. These are bits of solid geology. These stick up into high altitudes. They're kind of subject to wind, rain, snow, ice, you name it, not to mention tourists trampling them. All of that kind of starts to break that solid geology apart into a detrital sediment or a sort of series of particulates. These kind of get washed or blown downhill and accumulate as a series of sediments that basically go under the name of superficial geology, and always sit on top of the genuine solid geology. So when it comes to kind of uranium, the majority of material, uranium minerals, sit in your solid geology, but there are some that actually sit in your superficial geology, and we will have a look at one of these kind of rare occurrences of uranium in superficial geology a little bit later on. So that's kind of one part of the geology for you. This kind of, believe it or not, relates to ore body geometry. So this is kind of what can make ore bodies profitable or not. It's their kind of 3D shape. What is their kind of shape in terms of how deep they are below the ground, their width and their length. And I've just put in here this rather stunning cutaway diagram of Dungeness B to try and act as an analogy of that for you. So here you've got basically Dungeness B. I think Dungeness B is just about operating still, although I think it's soon going to be heading for decommissioning. So this is down on Dungeness Point in southern England. Dungeness B, one of only two power stations that aren't actually built on solid geology. So Dungeness B is built on superficial geology. So underneath this concrete base, you've got masses of piles that are basically drilled down into this pebble bank here that's been washed up by the English Channel. And that's how this structure bears its weight. It's through friction. It's born on piles that create friction between that superficial gravel geology and the pile itself, and that's enabled Dungeness B and Dungeness A to stay up all over these years. But they're quite unique in that they're not actually built upon the solid or bedrock geology. Anyway, that is a little bit of a digression. It's just here because if you kind of think of this, this is a 3D object. It has length A, it has depth or width B, and it's got C, height. In this case, it's height above ground, but if you think about this below ground, you can perhaps begin to get an idea why the 3D shape or 3D geometry of ore deposits is important, because basically how much waste material that doesn't contain uranium affects the profitability of an ore body. If your ore body is kind of incredibly thin and incredibly long, say like a piece of spaghetti, then you could have to excavate a lot of rock that doesn't contain uranium to get that piece of spaghetti out, and so your mine is not going to be that profitable. You're going to have a huge amount of costs. When if your ore body was more compact, less spread out, it could be more profitable. So you basically have to kind of link the 3D geometry of an ore deposit to its economic viability. And the deeper it is below ground actually affects your mining techniques as well, because with depth there are only certain mining techniques that work as well, and some of these are more expensive than others. Another kind of geological thing to kind of get your head around is the Earth is kind of a dynamic planet. Because the kind of human lifespan's quite short at circa 70 to 80 years, we tend to not appreciate geology actually taking place unless it's kind of flooding or landslides. We tend not to realise there's kind of processes going on in the background. And if you look back over the incredibly long history, geological history of the Earth, which is kind of 4,600 millions of years old, right back to here, then the kind of depositional environments for rocks is not the same as it was at the moment. So if you go back far enough, there was no oxygen in the atmosphere. Oxygen entered the atmosphere as a waste product from photosynthesis from the development of forests during the Carboniferous period. So the geochemical processes for vast amounts of geological time weren't the same as they are today. And this kind of explains why some types of depositional environments for uranium existed that no longer exist today. Just to take you kind of through this diagram here, this is basically an attempt by the United States Geological Survey to convey the entirety of human time. So back down here in this kind of little dot, you've got the Earth coalescing, sort of at the start of its birth, 4,600 million years ago. So it coalesces from dust in the solar system, or what was developing as the solar system, comes together as a solid planet, and then on this timeline it kind of spirals out all the way up to where we are today at this end here in the Holocene period here. And what you can see on this is kind of an attempt to sort of depict the amount of life around in that period, both in times of sort of creepy crawly creatures and in also in terms of plant. And there's also an attempt to put geological processes in here. So for the majority of time, we were kind of in the Precambrian period, and there wasn't much around animal life-wise until we kind of evolved into sort of single cellular, then multicellular species. These kind of increased through the Cambrian period, through the Ordovician period, and then kind of early Devonian, we begin to have plants evolving on dry land, and this injection of oxygen into the atmosphere. You can fit in various episodes of dinosaur extinction, possibly a little bit later than that in the Jurassic period, various periods of extreme volcanicity, ejecting liquid rock, igneous rock onto the surface of the Earth, more dinosaurs, a very, very early massive ice age, and then up to the quite recent ice age that we've just been through. So from this, the kind of important thing is to realise that the Earth isn't really static. It's our kind of human lifespan that makes us perceive it as being static. But there is plenty of evidence in the rock record that the geological history of the Earth is quite different, has been quite different from what it is now. And that explains why, particularly with Mesosomite uranium deposits, to be honest, it's best guess as to how they formed, because those conditions no longer exist on Earth. So the first one that we kind of have a look at for geological depositional environments is what they call inconformity related deposits, and this is kind of a pictorial representation that I've annotated. So this black wavy line across here is your actual unconformity. So an unconformity is kind of a concept more than an actual physical thing. So I've kind of put some text in here, but I'll kind of explain it to you. To have an unconformity, you first of all have a unit of rock number 1. That unit of rock kind of hangs around on the surface of planet Earth for a while, and it has the top shaved off it. It has the top eroded off it. So that's why you can see this kind of little fold in here, and it's kind of missing there. It's been eroded away by some form of geological process. So once that's then happened, you kind of again have a change in geological deposition, and you have rock number 2 being brought in sediment form and then changed into a solid rock. So the unconformity actually represents that period of erosion. So it isn't a thing, it's actually a concept. And so what it actually is that tiny, tiny, almost ephemeral gap in between rock unit number 1 and rock unit number 2. And when it comes to uniformity related deposits, they get deposited along this line, the line of the unconformity, because the properties of rock 2 and the properties of rock num are very, very different, and this causes deposition to happen along that unconformity line. So this is what one can look like. This one doesn't involve uranium, it's just basically an example of an unconformity. So if you look below the cursor, you will see this grey rock that's kind of stacked, pointing upwards. And you can see that all of a sudden, above this point, all your rock is kind of stacked horizontally. Well, at the bottom, this is rock number 1. Above, this is rock number 2. And this is the actual line of unconformity. Originally, number 1 would have gone right to the top of this picture, but it's had this top section eroded off, and then rock number 2 has been then deposited on top of that unconformity. And you can quite clearly see they're orientated different ways, they're different colours. It does say on here that basically this is a shelled rock at the bottom, and this is a sandstone rock at the top. So they're 2 completely different rock types. And that's the beauty of an unconformity. It kind of marries up across a distinct line 2 very different rock types. There's a couple of more exotic examples here. So this bottom picture is the Grand Canyon in the United States, and right across the middle of this picture that I've tried to pick out is an unconformity. Below here, you've got very, very old Precambrian age rocks, and above this conformity, you've got Cambrian age rocks. So there's no uranium in here. This is just a kind of example to show you how massive, how large unconformities can be. So a small scale one on the right and a large scale one on the left of the picture. And at the top here, this is one in the Wyoming. There's a difference in colour between the bottom below the unconformity and the top above the unconformity. So two different rock types able to be seen in that picture there, but not as distinct on this one on the right. So I've tried to pictorially represent this to you. So here you've got rock unit number 1. It's the oldest one. It's the one that arrives first. It sits round at point X. It gets its top chopped off. And then after a period of time, rock number 2 is then deposited on the top of that. And the unconformity is this almost invisible line. It's not really an actual physical thing between rock unit number 1 and rock unit number 2. And what quite often happens is that the properties of number 1 and number 2 are very, very different. So they have a different permeability. So that's the ability of fluid to move through the rock. They will have a different porosity, the ability to hold fluid. And they can often quite have a different chemistry as well. So what happens with mineralization, uranium mineralization, is you kind of have fluidized uranium coming through rock number 2. It kind of moves downward in response to gravity. It basically meets that unconformity. It goes through or about that line of the unconformity, and then it encounters the different conditions in rock unit number 1, and so then it fixes roughly about the line of that unconformity. So if you've got mineralization, you know that you've got mineralization about an unconformity line, and you can track that unconformity line in the geology, you can then predict out of the picture where further along that unconformity you might find uranium mineralization, and hence where you might extract it out of the ground. So an unconformity becomes quite an easy marker to spot, to harvest, as it were, uranium mineralization. In this example here, it's kind of, I've suggested that you've got hot uranium metal bearing fluids coming through some sort of porous rocks on the top, and you've got basically reducing conditions, often less permeable below here, which then fixes that uranium mineralization around that unconformity line. So this one, it would potentially be quite spread out, but so long as it's quite shallow, it could be cost effective to get that out of the ground. So predictability can produce profitability in this. So these tend to be in older rock types. You tend to get quite high grade ores associated with them. And the best examples really are Cigar Lake in Canada and also Ranger in Australia, which is coming to the end of its life. So this is a diagram to kind of explain the situation you've got in Canada. So Canada is kind of quite a big producer for uranium, although it doesn't have the biggest amount of resources. And I found this diagram on a bit of a dicky website, a bit of an unreliable website, but it's kind of quite a good picture to explain things to you. So here you've got a cross section below through the ground in Canada. It's showing you the geology. So this pink stuff is very, very old Precambrian rock. This light yellow stuff is the Athabasca sandstone, so it's permeable. And on top of that, you've got a shallow amount of glacial till, which is your superficial geology. So forget the horizontal thing that's not really to scale and kind of have a look at the this here. This is the depth below ground level, so that's the top of the ground, and that's kind of going down below the ground here. What it's trying to show to you are these red areas are different ore bodies that you have occurring along this line of the unconformity. So it's this kind of sub-horizontal line here that is the unconformity between this impermeable basement and this very permeable sandstone. So your mineralized uranium-bearing hot fluids have kind of migrated through the ground until they've encountered this unconformity, and then they've set round and about that unconformity line. I think there's actually some attempt here to actually show that different 3D geometries in here. So they're actually naming specific deposits here. So this is Key Lake, Rabbit Lake, Clough Lake, and Patterson Lake. I think these are all of these ones here. This is Sioux B, this is Sioux A, Sioux C, Jeb, McLean Lake, Midwest and Rough Rider, Cigar Lake down here, and MacArthur River. So, and in brackets here, you can see the percentage of uranium in these deposits. So round about 2, 2.5, 1-ish round about here, 2 coming up, 4.7 there, and then a huge jump for Cigar Lake. Cigar Lake's got 17.7% uranium. MacArthur's got 26.3% uranium. So really, really, these two are really kind of quite enriched. The other interesting thing about this diagram is this line across here, which it says line of open pit. So what this line is, it kind of marks the maximum depth to which you can extract material by open cast or open pit mining. So you excavate from the surface downwards by excavating a massive hole. So there's some depth at which that becomes financially unprofitable because it consumes too many resources to actually excavate that hole and bring the material to the surface. It also gets unfeasible in terms of geography, i.e. the actual size of the hole as well. So below this line, you basically have to use underground mining techniques to get the material out of the ground. So that's unconformity-based deposits. You also get vein deposits. So these aren't actually uranium deposits, but up in the top here, you can see some white veins and some veins with other mineralization along them. So veins are fractures within a rock body. So into these fractures, you can get hot fluids being injected, and dissolved into those hot fluids are minerals which then crystallize out. And in the case of uranium mineralization, those hot fluids obviously clearly contain uranium. So a vein deposit is what you call any deposit of uranium that forms in a void or a bedding plane or a fracture, as these ones here. So you basically have some areas within the veins that can be very, very ore rich, but you've got a background body of non-ore bearing rock, and whether it's profitable or not depends on the content of your desired mineral within the vein. If that content's high, it can make it profitable. If that's low, i.e. it's low grade oil, it becomes unprofitable. You can get vein deposits in any type of rock where you've kind of had a fracture and where hot minerals are percolated through and solidified. Where do these come from? Hydrothermal or geothermal activity, so from out of the inside of the earth. So what you get in terms of parts per million can be incredibly variable. It's usually uranite and pranorite that occur in this form, and you get vein deposits anywhere in the world. The UK's sole uranium mine at South Terrace down in Cornwall was a vein type deposit. So this kind of operated round about the Victorian period. At South Terrace, there was circa, they think, 750 metric tons coming out of South Terrace. The interesting thing with South Terrace is that it was South Terrace that supplied the ore for Marie Curie. So if you think about what Marie Curie did, isolating radium and then the other minerals for it, she started that work off initially with material that came out of the South Terrace mine in Cornwall. South Terrace wasn't originally a uranium mine. It was actually an iron ore mine. They discovered that it contained uranium, and it had an incredibly large amount of uranium. The veins were up to 31% uranium, which is really, really quite high. So they did initially close down this mine, but then they reopened it and they actually reworked the spoil heaps looking for more uranium. And out of that, they managed to get 286 tons of uranite. So it's kind of quite interesting, that I think, the link to Marie Curie. And that's kind of what it looks like coming out of the ground of South Terrace. It doesn't really say a lot, does it? It's a lump of rock. Some of them do look more interesting, as we'll see in a tick, like this one here. So this is also out of South Terrace. So this is the inside of a mineral vein, had a small vein, and when they broke up this, they actually found these intact minerals, beautiful, somewhat lurid green minerals of a uranium mineral called torbanite, locally known as green gym. And you can perhaps see why it was called green. It's kind of quite lurid. Green gym is one of the forms of uranium mineral that came out of South Terrace, and this one got preserved because it's a good specimen of mineral. So South Terrace was quite extensive. It had kind of one uranium vein going through it, or lode is what they call it in the local language. Although it's kind of doesn't really exist now, there's a few heaps of spoil. It's mostly been taken down. If you want to, you can kind of Google it and you'll find there's urban explorers doing YouTube videos with Geiger counters going there. The issue with this site is it is actually a site that's known to be radiologically contaminated because of those heaps of spoil at the top. How hazardous it is, I don't really know. It is recorded with Cornwall County Council as being a radiologically contaminated site, but it's kind of off the record, and it's not really open for the public. I don't think there's any actual plans to remediate it. It's all down to how long you spend there and what you do there as to whether it's going to injure your physical health, but it's privately owned, and entering the area does constitute trespass on that one. Health and safety, as with most things Victorian, a little bit interesting. So here's the kind of top of the mine and the headworks, and it's all balanced on a heap of spoil. This is partially what they reworked to get that extra material out of the ground for that. So that's your vein deposits. Another one we should have a look at is the sandstone hosted deposits. So if you have a little sort of look at these pictograms here, your layers of sandstone are these purple things going across it, the lines going across these little pictograms. This sandstone is in close proximity to some form of igneous rock, whether that's kind of a volcano or a dike or a cap. In that igneous rock, you've got some form of uranium, and if you have oxidized fluids taking the uranium out of that igneous rock and the sandstone, they will then crystallize in the sandstone as these green blobs round and about within the sandstone, but round and about that kind of igneous origin. With these, you get many different forms, and it's usually geochemistry that precipitates this fluid, this hot fluid within the sandstones. The issue with these different forms is that they've got that different 3D geometry, and that 3D geometry can basically affect their profitability. So for the record, you can have what they call roll front sandstone deposits, which are kind of crescent shape. You can have tabular ones, which are elongate and a little bit spotty, irregular. You can have basal channel ones that used to be a formal watercourse, so they kind of have the shape of a watercourse. And then you can have tectonic ones, which really have a variety of shapes. So sometimes in geology, if you can predict that shape, if you can work out what it is, you can predict that 3D geometry and work out not only where to excavate for the deposit, but also whether it's going to be profitable. So these are things that all geologists look for. What shape is that 3D geology? Where's the mineral of interest liable to be? And is it going to be profitable to get out of the ground or not? So these sandstones can be really any age. They can have any kind of concentration of uranite, and they in different forms have kind of been excavated across the globe, really. And it's worth mentioning here, I kind of did touch on geological history, but each country has its own geological history. What you've got in terms of rock type and what experiences, geologically speaking, a country has had, it's not going to be the same, for example, for Japan as it is for the UK. It's not going to be the same for, say, South Africa as the Russian Federation. It depends where you are on the globe. So really, when it comes to ore deposits, it's kind of very, very unique, each one. You can draw commonalities, but just because you find one type of deposit in, say, China, it doesn't mean that you can apply those lessons to another deposit somewhere else, unless that is a deposit of a similar type. So if your geological history has involved lots of igneous action, then and sandstone deposition, you could have those types of deposits. It all depends on what your geological history has been. So the IEA also mentions igneous deposits. So these divide into two types. Igneous deposits that remain below the ground surface and slowly cool and solidify. And again, Rossing Mine in Namibia is kind of the prime example here. The problem with these is that uranium's often bound up with other minerals, which makes it very difficult to extract, or can make it difficult to extract. So these are the ones that never quite reach the Earth's surface. They always kind of stay just below the Earth's surface. And then you get the ones that kind of come up in volcanoes. So if you think about your volcano kind of belching liquid rock, some of that liquid rock coming up these days could contain liquid uranium. So that could be deposited close to that volcano. So your grades can vary, but the deposits physically tend to be quite small. So if it's small and low grade, it may be not possible to turn a profit up here. And at the top of the picture, this is just an example. It's a stick of rock core drilled out from a granite, just to show you really what granite core looks like. So this is kind of an intrusive igneous rock, and you can see in here some different colors, so there will be some minerals bound up with that. Yeah, and you've got the Stravos caldera in Russia as an example of that type. You also, in some countries, get what they call breccia complex deposits. These are kind of quite difficult to understand, but simply you need a large land mass. So you need something like continental Europe, continental Australia, continental America, or Canada. This land mass gets stretched apart, and basically part of the ground stays in its original position, the horst, and part of the ground drops down, the graben. So This happens kind of coming across from the Rockies, from sort of California into the sort of Midwest parts of the United States. Same is true in Canada. So what happens is that you've obviously got a fault line that kind of develops between the Horst and the Graben, picked out here by these black arrows. So the rock gets ground out as these movement occurs, forming a breccia, a kind of rock rubble. That's what a breccia is. And then you can get mineralization coming into that rock rubble and precipitating along that fault line, with that uranium coming from different potential processes. So they tend to be kind of quite geographically limited, i.e. concentrated in one space. They tend to be quite permeable, and so they're kind of easy, relatively easy to kind of pick out geologically. And this is what Olympic Dam is one of these. It contains uranium, but Olympic Dam is what you call polymetallic. It's got more than one mineral in there, so you've got iron, copper, gold, silver, and rare earth elements. So Olympic Dam isn't extracted just for the uranium. The uranium is actually a byproduct. It's actually extracted largely, I think, because of the iron and the copper and the silver. You may as well just precipitate the uranium and take that as a bonus, as it were. So it wouldn't be economic for the uranium, but the other elements make it profitable to get that out of the ground. So Horst and Graben can be quite extensive, but the actual individual deposits tend to be kind of quite close in terms of geography. So another one in here, your quartz-pedal conglomerates. So there's a picture of one down here. So these browny things are your quartz pebbles, and it's held in a conglomerate body. The conglomerate body is this grey thing that sticks it all together. Don't quite know how these are formed, because it's one of these where we no longer have the same sort of environment. So it's a little bit difficult to work this out. There's two opposing theories, but I don't think they're extensively worked at the moment. Again, another one where we're not entirely sure how they form, what they call metasomite deposits. So these are incredibly old rocks. So they date back to those early years of the Earth's history. So phenomenally old. Obviously, nobody was around in those days, so we kind of have to piece the record together. All the currently worked deposits are in Ukraine, and the amount you get is variable. This little diagram up here is just up here for interest. So this is basically an outline of Wales. The Roman name for Wales was Cambria. Much of what we know about Precambrian and Cambrian history kind of was worked out by the Victorians in Wales. This old name of Wales, Cambria, actually gives its name to the period of time known as the Cambrian period, and hence it also gives its name to the Precambrian period. So that's just kind of in there for a little bit of interest. Okay, so those are your kind of types of deposits you get in your solid geology. You also get deposits, not as often, in your superficial geology. So these are actually within sediments, and these are called your superficial deposits. So these are near surface deposits. In fact, can be at or just below the surface. So they're not in solid rock, they're kind of held in sediment. And a big example is Langerheinrich in Namibia, and we'll go and have a look at that now. So Langerheinrich, some areas are rich, some areas are poor, and I'll kind of explain how they work out where to mine that. So if we just go back to this diagram, everything we've looked at is kind of in this deeper solid geology. Superficial deposits are in this shallow category of superficial geology. of which Langer Heinrich is a kind of prime example of this. So Langer Heinrich mines in Namibia. Namibia's kind of not overtly developed, and Langer Heinrich's kind of really in the middle of nowhere. This is kind of the picture for it. So here's the mine in the middle. There's some of their processing water, and if you look in the background, you can see it looks a bit hummocky. You can see some mined out terraces here, and this is where they've been taking out the uranium bearing material and mining. You can also see there's some kind of build up here, and this is where they're building up their waste material. So at first you think, oh, well, it's not very kind of intrusive on the landscape, it hasn't kind of had much effect, but the more you see it, you see that there's this kind of huge lighter brown area against the darker brown and greenier brown. So it does actually kind of geographically affect kind of quite a large area here. And this is kind of a little bit more of a close-up here. You can perhaps see all of these mine terraces back here and waste deposits being made here. This is kind of the actual processing headwork. So in here you've got your kind of mixing tanks and your ion exchange columns. And there you've got the kind of river coming by. So if some of these pop, it's this river that's kind of going to get polluted here. But yeah, you can see a little bit better how much more it's taken away in the background there. They send out one. This is what this is. It basically blasts down a borehole and returns some samples up to the surface, and you can see this long line of samples. And then they come along and they prospect these bags. So what they're doing by using these lorry-mounted drilling rigs is they're basically prospecting, and they're looking for the highest parts per million, because obviously that's going to be the most profitable area to excavate. So they use that technique to decide where they're going to excavate, and then they bring in the machinery. The machinery just basically digs away these very loose superficial sediments. It's not that hard, physically hard to do this. It's kind of just like excavating in sand, really. So they do that. It gets basically put onto the back of a dumper truck. That dumper truck then basically transports it to the headworks, where they basically give it a bit of a wash, shake it out, and then send it to a crushing plant where it gets crushed, and it kind of comes out as a lot more finer, powdery material. And then that kind of goes on into the onwards treatment process, where they basically mix it with water, put it through an ion exchange column, and then eventually precipitate it out. So because you're kind of quite isolated here in the middle of nowhere in Namibia, it makes sense to kind of take it towards the end stage of the product, rather than sending a large volume of rock away for processing 1,000 miles away. So you're taking away a concentrate, so you transport away something that's very pure, rather than something that also contains a lot of waste material. And that's one thing that kind of can affect the profitability of this. Think about your supply chain lengths. You know, ion exchange columns, chemical processes, they need a lot of materials, so it's got to be profitable to bring that in via a supply chain, and the longer that supply chain is, the more it's going to cost you. So there's operating costs behind all of this, which can influence the profitability of a mining process. So that's just kind of a shot to show you what it looks like at night. It's kind of, you know, quite a lot going on in here. Again, another thing, just think about all the power to run all of this lights, but also all of this machinery. How is it powered? How is electricity generated? You know, is it running on diesel generators, and how much are they costing to power all of this? So all of these things kind of influence the profitability. Where the Langer Heinrich mine tends to win out is that all of the uranium is quite shallow in this landscape here, so they don't actually have to excavate much, and by using those drilling rigs they can kind of ensure that they take away the top grades, the highest parts per million, to be reprocessed, rather than having to remove lots of rubbish and waste material to get at the good stuff, as it were. More processing costs. So this is kind of where they're building up the waste material left after crushing and after extraction. So you can see these being brought in and these terraces being built up, and these are kind of individual dumps of waste material, so it kind of looks quite ugly. In the background here you can see a tailings dam, and I think this blue one's where they keep their water once it's been taken out of that tailings dam. So there is a little bit of sustainability in here, in that you can dewater the tailings dams and recycle fluids in the process to some extent, but I'll kind of get onto the future with some issues over tailing dams on that. I'd encourage you also to look at the Rossing mine. So this was worked last week. Unfortunately, the images are too low grade to actually make it useful for a PowerPoint, but if you follow that link there, you'll come down, have a breakdown of the Rossing mine, also in Namibia. And this is a below ground level mine. This is a deep mine here that they use for that. Okay, so having looked at the Langer Heinrich, let's kind of think about different mining techniques. There's essentially, bottom of the page here, 3 different mining techniques involved for uranium. You have open pit or open cast, which is kind of what we looked at in relation to Canada. You've got underground mining, and you've also got something called in situ leaching. So these are the 3 primary techniques. So what is used at a site depends on the grade or the parts per million of uranium, the depth of that ore body and its lateral spread, so that's its 3D geometry, as it were, and also the permeability of the rock that the uranium sits in and the surrounding rock as well. As of the moment, 2019, latest figures available from World Nuclear, in situ leaching is taking a massive lead of just under 60% of uranium produced in 2019. So just under 60% of uranium produced in 2019 is via the in situ leaching method, and I'll get onto that into a sec. 36% of it is combined deep mining, underground mining, and open pit or open cast. And 7% of that is by a byproduct method, where they're not actually specifying which mining technique it is. And this is kind of quite interesting, and we'll kind of come back to the changing percentages in a little bit. But let's just kind of consider those techniques. So your open pit or your open cast, Americans tend to call it open pit. Open cast tends to be what's called in the UK. It's basically where you dig and excavate a large hole using, if needed, blasting techniques and machinery to take away that rubble and process it, usually close by. Hence, you usually find piles of waste material accumulating. So if you think back to that kind of Canada thing, there is a depth to which you can go with this. Either this hole will kind of just get ginormous, and I would have a Google of Bingham copper mine. That hole is just enormous in the United States. So it's either going to become unprofitable because of the depth or the kind of size of the hole. You know, it's not profitable if you've got lorry drivers driving 2 hours to get out of this to where they're going to take the material. So it's things like that that tend to knock open pit on the head, as well as planners kind of getting a little bit leery about the actual size of the hole. So it is kind of a feasible technique, but at some point it does kind of get unfeasible. So that's your number 1 here, your open pit. Number 2 is your traditional underground mine. So for this, you've kind of got to think about how coal was extracted in the UK, really up until the kind of 1980s, when they really began to not deep mining underneath underground on the head. Sorry. So you basically got a set of headworks. And these headworks basically contain shafts that are driven vertically downwards. You've got to have in UK law 2 means of ingress and egress, so you need 2 shafts, and then you drive adits off these shafts, and where these adits go is all dependent on where the predictions are that the mineral actually is underneath the ground. You then send miners down, they excavate the rock, it comes back up to the top, and then it's kind of the minerals excavated out of it. So both the open cast and the underground mine actually involve people accessing the geology. And one of the reasons why in situ leaching is kind of taking over is actually because of the health and safety aspects. Because in situ leaching does not involve people accessing the geology. Everything is done remotely from the ground surface. And what you do with in situ leaching is you put down 2 networks of boreholes. So you've got a series of a network of injection wells and a network of production wells. You put them down into the geology wherever your uranium is predicted to be, and then you pump down some sort of mobilizing fluid through your injection wells. That then liquidizes and mobilizes your uranium, and you then pump up that liquidized uranium through your wells up onto the surface. And that's brilliant in terms of health and safety. The problem with in situ leaching is that it's not suitable for every single type of uranium occurrence. So it's only suitable in certain certain locations. This here is just a combination diagram. So this here, it doesn't show you in situ leaching. It shows you kind of a cutaway of an open cast mine, and then alongside that your traditional deep underground mine with its vertical shaft and the adits kind of coming across. So I've put in this pink line across here. So below the pink line, it's no longer economically feasible or practical to operate open cast. So you've basically got to switch to deep mining. And this certainly was the case until about 10 years ago, when in situ leaching really took off as being a much more feasible method. There is, in practical terms, you could probably easily go down to 500 meters with in situ leaching, and it would still be profitable, and obviously clearly safer, because you haven't got to send people down that far. So the typical open cast mines, you've got Ranger in Australia, which is kind of coming to the end of its work. You've got Rossing, which also has a deep element to it, are the good examples. And what you do with the open cast mine, you literally drill and blast. You basically then take that broken ore away. Again, with Langer Heinrich, you crush it, you mill it, and you take the material out. Whether you take a concentrate out or whether you just kind of transport it to elsewhere, it all depends on where you actually are. Langer Heinrich's in the middle of nowhere, so it makes sense to reprocess on site. And at Langer Heinrich, because it's all superficial sediment, it's not actually solid rock, you don't have to drill and blast. All you need to do is excavate it. Langer Heinrich is just like sending an excavator onto Blackpool Beach. The stuff is not held together, it's loose sediment, you can just dig it up. And technically you could you could actually use a spade. So in 2008, 20% was coming out of open cast. It's difficult to find a value for this that is up to date. All I can find is this single table here, which is saying that if you combine underground and open pit, you're having a maximum of 36%. So basically from this, if you add up open cast and underground mining, you realise that what's happened recently over the past 5 years is there's been a vast increase in the amount of in situ leaching, and this is taking over as the primary form of extraction. So with underground mining, basically in 2008 it's 42%. So these values don't add up, and there's not a breakdown available for exactly how much comes out in terms of uranium for open cast and underground. We just have this combined figure here, but it doesn't add up. What does stand out is the fact that in situ leaching is kind of the really increasingly common technique these days, and we'll kind of you'll understand why in a few slides time. So with underground mine, it's a traditional form of mining for practically about everything, but these days health and safety is coming increasingly to the fore, as it should be. And what is happening is that if you're in a country with a strong health and safety regulatory body, underground mining is kind of very much on the decline. You would have to wonder if whether you're exporting your resource acquisition overseas, potentially to countries with a lesser standard of health and safety, but that's entirely a different subject to cover here. What has happened specifically in relation to underground mining and uranium is automation. So in some mines, if you've got the correct ore body geometry, you can make it semi-automated. So this is what they're basically doing at MacArthur River. They're basically limiting human interaction underneath the ground, and they're automating the process as much as possible. But you cannot do this for every single ore body geometry. So what they do is they have two adits. They basically mine upwards and bring it down onto a remote low loader that then brings it up to the surface. And they're also looking at doing that with slurification as well, and jet boring at Cigar Lake. So even underground mining is kind of bringing about some innovative techniques. They are obviously profitable at the moment because they've got an incredibly high parts per million at those particular location. So thinking about mining hazards, quite clearly, I think everybody will be kind of familiar thinking about the radiological hazards, but you've also just got bog standard health and safety, which says that human beings entering confined spaces which could potentially collapse is a hazard. It can be dangerous. It has been dangerous. The history books, and still up until I think 2013, there were deaths taking place in the UK from underground mining. So mining is just quite simply hazardous enough without kind of adding a radiological element in there. But the more you automate it, hopefully you can control human access and perhaps make it somewhat safer. So you do already have, if you think about it, naturally occurring radionuclides in certain rocks. So if you've also got uranium mineralization in there, there is a potential for an increased exposure, particularly on underground mines. How can you manage that? Well, airflow control, air exchange is very big in mines. Partly it's to reduce particulate debris, but silicosis, or miner's lung, has been quite a big health hazard for some years now. And in fact, it was the German miners in around about 1500 actually discovered the existence of radon, although it wasn't isolated until much later. In the Black Forest in Germany, they had a miner's disease basically known as black lung, and it was basically a combination of silicosis and radon exposure. that basically meant they had very, very short lifespans. So with underground mines, you've got collapse, you've got particulate inhalation, you've got all sorts of things going on there, or can potentially have all sorts of things. So it's a hazardous working environment. Automation can help, but it's not exactly a total solution. And it's partly that kind of health and safety aspects and the ease of carrying out in situ leaching, I think, that's kind of led to it being a far more common technique. So technically for in situ leaching, and you can actually have something called heap leaching of previously excavated material onto an impermeable membrane, which is just a derivative of in situ leaching. It's ex situ technically, but it's the same sort of thing above ground. So in situ leaching, it takes below the ground, so below the ground surface. So technically you need a permeable ore body, so it's got to be something like a sandstone that contains uranium, and it's got to be permeable, because what you do is that when you drill your borehole network, you inject it with your dissolution solution. That dissolution solution, and it depends on the geochemistry which one you use, liquefies your uranium, and then you pump that back out of the ground. So the benefit of in situ leaching is you haven't got human beings entering the ground. You're only accessing the ground via surface excavated boreholes, and all you're pumping down are liquids, and all you're taking back up is liquids. So you're leaving the vast amount of rock in situ. So it actually benefits you in terms of waste, as well as human health and safety, as it were. The problem with in situ leaching is actually ensuring that that corrosive or potentially corrosive leaching solution stays in place and doesn't move off elsewhere in the geology. And this is the issue. In many areas of the world, the underground geology contains water-bearing rocks, commonly referred to as aquifers. And in many of these areas, these aquifers actually provide the local drinking water and or industrial water as well. So if you're carrying out in situ leaching, you have to be careful not to get your leaching fluids mixed up with groundwater in aquifers. If you do, you basically contaminate your aquifer, and it might mean that aquifer is no longer usable, or it might mean that that aquifer's got to be cleaned up. So that's what I mean by saying that in situ leaching is a brilliant idea, but it doesn't work everywhere. There are some areas where it's not going to be a feasible technique, because you might have a strong environmental regulator who says, no, you're not doing it. So these are kind of diagrams to perhaps explain it a little bit better than I can. So let's have a look at this one on the right hand side. I think it's better. So you've got a series of vertically aligned wells, a network of these. On this one on the right hand side, you've got a series of blue wells where you're injecting your leaching fluid, and then you're recovering that fluid back up to the ground surface once it's leached out the uranium. So that fluid's coming back up the red well network, carrying the uranium, and then you basically process it through some form of industrial process to actually get the uranium out of that fluid. You can recirculate around and around and around. That's perfectly feasible. You can actually clean these fluids up in between times as well. And if you look at this kind of diagram here, it shows you this bright yellow or brightish yellow uranium ore body in a permeable sandstone. And that is bounded by underneath by a clay and on top by a clay. And this is a kind of sketch diagram here. The clays are impermeable, so these hot leaching fluids will only stay within this yellow band. They won't escape from that yellow band because the hydrogeological properties of these clays confine it to that yellow band. So that is exactly the sort of situation where you can use in situ leaching. Similarly on this one here, you've got some sands with the uranium in them, and then you've got clay preventing that leaching fluid from going out of those permeable uranium bearing bands. So now in 2019, we've got just under 60% of uranium coming out by in situ leaching. A lot of it in the USA, Kazakhstan, and Uzbekistan, also Australia. The example we're going to have a look at is from Australia and other places. And, you know, World Nuclear says it's seen as the most cost-effective and environmentally acceptable method of mining. Another experience supports this. And it is cost-effective. You haven't got human ingress. You know, it's cheap to drill boreholes and install a plant. So I had a look back at previous versions of this PowerPoint, and so I've been doing this since 2008. So in 2008, 28% by in situ leaching. I didn't have any figures for the years in between. 2017, 50, 55, and then up to 50%. So it's literally shot up in recent years to become the preferred method. And it sounds all very good. It sounds brilliant, but I think there's a problem in that I'm not sure that all countries that are carrying out in situ leaching are equally environmentally responsible. And by that, I mean that they may not have an effective environmental regulator that looks after aquifers and prevents them from getting polluted. So what I think is happening, and I will say I don't have any proof of it, but I would say that in some of these countries that are now carrying out in situ leaching, it's quite possible that they're carrying this out where that leaching solution isn't confined geologically and is probably getting out into the wider environment with a potential to cause pollution. So that's just kind of, you know, my gut feeling that you haven't got something now in this picture that's green that actually confines this leaching fluid and keeps it trapped between two layers of geology. In Australia, where this example is from, the Beverley mine, you've got a big, environmental regulator who monitors this and makes sure that any aquifers underneath the ground are protected. But is that true in all areas of the Russian Federation, for example? I don't know, but I would imagine that, you know, best guess is probably not. So here, this is basically the Beverley one. You've got your injecting wells and you've got your wells recovering that mobilized uranium solution. It's very neat. It looks like a huge footprint at the surface, but it isn't. All of this can be quite easily decommissioned and taken away. It's generally kind of quite a good solution. And here in the bottom left, this is straight off World Nuclear. This is actually the Beverley field here. There's not much infrastructure other than a few kind of headstanding type things, which are quite easily decommissioned. And these boreholes decommissioned back by filling them full of concrete once it's finished. There's a good explanation of this on World Nuclear. I'd suggest you kind of follow that up on that one. But yeah, this is my thing. I'm not convinced that this is always present in some countries where you've got a weak environmental regulator. That's kind of my bugbear. That last category of mining as a co-product or byproduct, depends which country you're in, different things used. UK tends to talk about it as a byproduct. So Now we've got 17% of uranium coming out as a byproduct. A prime example being Olympic Dam, where it's just literally almost a side recovery through various techniques because you've got so many other things in there. Other byproducts used to get uranium out of phosphate fertilizer, and this was the reason for high levels of radiation in Whitehaven Harbour. So a few years ago, when they wanted to develop Whitehaven and develop Whitehaven Marina, they basically carried out a survey and they found that it had quite high levels of radioactivity. And the kind of first thought was, oh, this is Sellafield. But that wasn't actually the case. In Whitehaven, you used to have a soap powder manufacturer, and they basically used to use mined phosphates to make soap powder out of, the stuff you put in washing machines. And basically, they used to discharge into Whitehaven Harbour, and in those phosphates, you basically had high levels of norm, and that's where that norm contamination came from the soap powder manufacturer that has ceased functioning about 30 years earlier. So there used to be quite a lot coming out of that, but that's no longer economic viable. You also get it coming out as a byproduct along with rare earth elements. And there is some coming out of Greenland now. So Greenland's a new area of interest for mining for very unusual rare earth elements, iridium and things like that, the things that make mobile phones and electric car batteries tick. And uranium, I think, is a byproduct from some of the Greenland mines as well. And as the Greenland ice sheet kind of melts and retreats, that's kind of exposing more and more geology in Greenland. It looks like they could actually have a serious income from that. So the suggestion was a couple of years ago that Greenland may achieve independence from Denmark as a result of mining its geology. I don't know how far along that's got. If you look at mines by output, so this is the kind of this year's figure. So the single highest mine putting out the greatest percentage is Cigar Lake in Canada. So this is where Canada kind of slides to the top of that production table. If you look at it per mine as opposed to per country. If it's per mine, Canada rules. If it's per country, Kazakhstan rules because Kazakhstan's got more mines putting out quite a high percentage, but not individually as high as Canada, if you get it. But this does kind of slide around year by year, I think. So not, there you are. They've got, this is in terms of companies, actually, by the way. So these are the names that kind of produce it all. Rio Tinto, the British company, coming in quite low down. And some of these, to be honest, never really heard of. But yeah, there's different ways of looking at it. I had to think about the kind of environmental aspects, and those still awake will spot that this is not actually entirely the environmental aspects. I think if you think about it in terms of environmental aspects, you've got the waste products from this to deal with that could affect your profitability. So this could be rock, could be sludge, could be liquids, or could be gaseous. And obviously, an environmentally responsible country, you're going to need waste permitting to dispose of that. So that's kind of quite a big thought for that. So the waste is a big part of the environmental picture. You've also got environmental pollution created by the mining process. So that could be permitted discharges to water or air. Technically, that isn't pollution, but it's still kind of an end product type of thing. You could have leakages of waste into the environment, and you could have escape of leaching fluids during leaching as well, that sort of thing in there, depending on what that waste form actually is. So wastes are a large group on their own, and various forms of waste can actually cause environmental pollution as well. So that's kind of two big influences on uranium mining. depending on how strong your environmental regulator is. And then you kind of got health and safety. It's just a physical thing, you know, particularly with open cast and underground mining. So you've got physical hazards, you've got to have radon hazards in underground mines, and then you can have collapse on underground mines and particulate hazards as well. There's lots of kind of health and safety implications in there. And then you've kind of got to think about how the world is changing. So if you think about the government's UK government's white paper on energy published 2012, that kind of makes interesting reading. It's not that long. And they're basically pushing carbon reduction and this desirable thing of achieving net zero. So basically, a lot of operators are being pushed to achieve carbon neutrality in what they do and in their supply chains. So this is a big thing in civil engineering at the moment, is looking at the carbon neutrality of construction. And that also includes mineral extraction as well. So you're going to have the big mining companies basically trying to achieve carbon net zero. And what is going to be the impact on that, on uranium mining? It's too early to tell, so I don't really know. What I do think is that these producers we've had a look at will basically be carbon counting what their processes actually are. Okay, also kind of feeding into that, if we consider onwards processing, so I'm never sure if this is part of milling or whether it's part of uranium mining, but I thought I'd just mention this because it kind of ties in with the geology. You've got issues with your onwards processing, again, your waste, environmental pollution, usually due to poor waste management, and clearly health and safety. And the big thing that kind of ties into the sort of areas I work in is tailings disposal. So after you've got the stuff out and you've crushed it and you've leached it and you've separated it off, you're kind of left with solids and liquidized sludges. Your liquidized sludges go into a kind of tailings disposal dam or a tailings dam for a short period. Often they're dewatered, and these tailings dams are incredibly unstable. So if you look top right here, here's a kind of schematic of one. So they're usually excavated into the geology or made out of geology making buns. They sometimes have a liner in them. And in here you pump your sludges and you dewater this. You can actually recycle processed water through this. But the problem is that wherever you get man-made buns that are deliberately engineered and water, there is the potential for them to desolidify and collapse. And so the contents of the tailings dams can basically fail to be contained and gush out, and often with fatal consequences. So you basically have a rush of fluidized sludge. That fluidized sludge may contain contaminants, but just having a fluidized sludge is hazardous enough on itself. I would recommend that you Google worldminetailingfailures.org. I can't play it to you because it's not going to work on this recording. So Google world mine tailing failures, and you will see a video on that page of what happened in 2015 when a tailing dam collapsed in Brazil, and the flow of fluid from that containment dam killed 13 people. It's not pretty. It shows you what a real danger these things can be. If you want to know when the last tailings dam collapse was in the UK, considering that the UK is supposed to be reasonable on health and safety, it was 2009. So it's just the congruent instability of man-made geology and liquid. Sooner or later it can basically give way. Doesn't have to, but it's quite likely. There's a useful website called wise-uranium.org. It's an old-fashioned website, but it shows you lots of photographs of uranium mines of all sorts. And on here I got this kind of litany of major tailing dam failures. So they're kind of a known civil engineering hazard, and they can be fatal. So have a look at those two websites. I'm not an expert on exposure, but World Nuclear's got something useful on exposure from radiation during the mining process. So I'd recommend you kind of follow up on that one. And to wrap up, the factors relevant to mineral or uranium extraction, to me, the geometry of the ore body is really important. You know, how deep is it? How much waste material might you have to shift? What's the size and the shape of it? What's that 3D geometry? What's the properties of the surrounding rock that it's held in? Is it easy to drill and blast, or is it incredibly hard to drill and blast? So the geometry and where it is and how deep it is really affects your profitability of any mineral extraction. The concentration of that desired mineral in the ore body, its parts per million. What's its mineralogy? Is it easy to process? Is it hard to process? What's going to be that cost of extraction? What's the cost of processing, and can it be processed? How much has to be processed to make it profitable? How much have you got onwards travel from that mine location to make it profitable? What's your market price? Uranium goes up and down, as does any other commodity. So you can have some short-term predictions, but how good are they? So you've got your current market value and the volatility of that commodity. You've got processing costs to chuck in there. You've got capital costs in there. You've got your operating costs, so maintaining this facility, things like diesel, wages, and then don't forget, many countries require sites to be restored afterwards. Maybe this is just filled in for open cast, but it could be making it as good as new, because the amount of restoration will vary from country to country. Then you've got regulatory control. You've got environmental management, so things like permits, whatever decommissioning and restoration requirements are required. What are the requirements on tailings dams? Are they allowed? Are they not allowed? You've got regulatory control on health and safety. How are you going to be allowed to operate? How's that going to affect your costs? All of these sorts of things to kind of be filtered in. And then an interesting one that comes in is land ownership. Ranger Mine in Australia, incredibly profitable, but it's in native ownership. And the native owners have said that they don't want the mine to be extended. So Ranger, once it's exhausted, is not going to be extended, it's going to be closed down. So that's another one that can be kind of geographically relevant. So all of these have basically got to be factored in to work out whether it is viable to mine uranium. So how cost effective it's going to be in relation to these factors. Obviously that kind of does depend on the market price, and uranium's just the same, you know. Just because a large part of the current nuclear industry with its current reactor setup runs off uranium isn't enough to actually make uranium mineable. It's not special, it just needs to be profitable to the people that actually get it out of the ground. And if they aren't going to make a profit out of it, they're not going to get it out of the ground just for the benefit of the nuclear industry. So there's a lot of outward influences on that, and that's why the kind of government's white paper published on energy, published in December 2020, is worth a read, and think about the kind of implications coming out of all of that. So these are some of the information I kind of used to put this together. You used to have a couple of BBC podcasts on minerals that are kind of worth a look at on there. That's that Wise Uranium. It's a kind of old-fashioned website, but it's sound and it works, and it's got a couple of voiceovers for you. You've got World Nuclear. They used a little bit on Ranger and Canadian techniques. And there's a kind of interesting poster presentation on radioactively contaminated sites from on there. And again, good mining pictures from Wise Uranium on that website. Okay, so that's it from me. I hope you enjoyed that. Please feel free to get in touch if you've got any questions. I'll try and well, just email me or just get in touch via Teams. Quite happy to have a face-to-face chat as well if you would rather do that. Okay, bye-bye from me. Hope you found it interesting.